Hi everyone, here is the second part of our chapter 10 and we can start talking about the acid catalyzed dehydration of an alcohol. So what is the meaning of dehydration? Dehydration is simply removing a water molecule. Okay, and we can do it in the presence of an acid catalyst. So this is the alcohol. In the presence of sulfuric acid, you heat it and you can get an alkene. Okay, so in the presence of sulfuric acid, alcohol forms an alkene and a water molecule, and this is called an elimination reaction. We are eliminating a water molecule, and here is the mechanism. Dehydration of secondary and tertiary alcohols are E1 reactions. Now, in fact, the very first experiment that we are going to do in the lab also follows the same procedure. We are going to dehydrate methyl cyclohexanol. Okay, now this is a cyclohexanol. What's going to happen? So this is the sulfuric acid and this is the mechanism. Lone pair on the oxygen is going to grab a proton from the sulfuric acid and going to protonate this oxygen. Now the oxygen has 3 bonds, making it a positively charged molecule. Okay. Once oxygen is protonated, it makes a good leaving group. So since the leaving group is water, it just falls off and forming a carbocation. Right? This is the carbocation. And then what's going to happen? The water molecule that just left act as a nucleophile or a base, act as a base to remove a proton from the beta carbon. So this is the alpha carbon, this is the beta carbon. Water molecule comes and takes the hydrogen and give the electrons in the bond, 2 electrons to form a bond between this carbon and this carbon. Now the carbocation charge will be neutralized by forming a double bond. So cyclohexanol became cyclohexene. That is the mechanism. And this dehydration is a regioselective reaction. What it means is if you have a unsymmetrical alcohol to begin with, you will get 2 products. And one of these are going to be a major product, the other one would be a minor product. Now here you have a tertiary alcohol. In the presence of sulfuric acid, the first thing is oxygen will get protonated, forms a water molecule, and then the water molecule falls off and then form a tertiary carbocation. Once the tertiary carbocation forms, there are 2 alkenes possible. So you can have the most substituted alkene form or the less substituted alkene form. Okay, so the carbocation, if the hydrogen, the water molecule, if it grabs a proton from this carbon, forms this major highly substituted alkene. If the hydrogen lost from this terminal carbon, it forms this terminal alkene, which is less stable, 16%. Same thing with this methyl cyclohexanol, 1 methyl, 1 cyclohexanol. Okay, so in the presence of sulfuric acid again, hydroxyl group will get protonated, forms a water molecule, it falls off, forms a carbocation right there. And this carbocation, so you can form a carbocation like this. That's your methyl group and then carbocation right there. And then you have a hydrogen here and also you have a hydrogen here. So one of these could be removed by the water molecule. If the water molecule takes this hydrogen and give its electrons to form the double bond, this will result in the formation of this product. And if the water molecule takes this hydrogen and form the double bond, this will give you the other product, which is this product, which is less substituted alkene, 7% of that, and then the more substituted alkene, 93%. The more stable alkene has the more stable transition state leading to its formation. So the first thing is protonation of the alcohol, forming a positively charged alcohol, and then carbocation forms by removing the water molecule, and from here it can take two paths: formation of the most substituted alkene or the less substituted alkene. Energetically, it's more favorable to form the more substituted alkene because it has less energy compared to the less substituted alkene. Okay. And this dehydration, meaning removal of a water molecule, is a reversible reaction. Now this is a starting alcohol. You remove a water molecule, alkene is formed, dehydration. And we can add a water molecule across the double bond to get back to the alcohol. To prevent the alkene from adding water and reforming the alcohol, the water is removed as it is formed. So we normally do a distillation, and this is similar to the very first experiment that we are going to do, which is dehydration of methyl cyclohexanol in the presence of a acid catalyst. You do a distillation. Through the distillation you can remove the alkene product formed as well as water molecules being formed. Otherwise it can go back to the original starting material because this is a reversible process. Tertiary alcohols are the easiest to dehydrate. Tertiary alcohol, there are 3 alkyl groups, and secondary alcohol has 2, and then primary alcohol has 1 alkyl group. The rate of dehydration depends on the ease of carbocation formation, and we know tertiary carbocation is the most stable because it has 3 methyl groups that can make it stabilize by donating electrons through hyperconjugation. Okay. An E1 reaction creates a carbocation intermediate, so watch out for carbocation rearrangements. Now what is E1 stands for? E1 is the elimination, 1 for the unimolecular. Okay. Now here you have an alcohol. This is a secondary alcohol. You add sulfuric acid. So we know what's happening when you add sulfuric acid. Alcohol will get protonated, forms a good leaving group, water, it leaves. So then a carbocation forms on this carbon. And this is a secondary carbocation. Now there is a possibility that this can rearrange to form a tertiary carbocation. How? By a methyl shift, 1,2 methyl shift. We don't have any hydrogens on this carbon. We have methyl groups. So one of the methyl groups going to move to the carbon. So you can see how it's going to move, and then it creates a tertiary carbocation. Now the secondary carbocation, if it doesn't rearrange during the elimination process, what's going to happen? You form this alkene. So one of the hydrogens on this carbon removes and form a double bond. And if the carbocation rearrangement takes place, there is a hydrogen on this carbon. You see this hydrogen will eliminate to form more stable, more substituted alkene, 64%. And then you can also have the other competing alkene, which is 1 hydrogen removed from this methyl group, making terminal alkene, which is 33%. Okay. Dehydration of a primary alcohol is an E2 reaction. The previous one that we were looking at, it was a tertiary alcohol, which is a E1 reaction. Now this is a primary alcohol. E2 means bimolecular elimination reaction. So in your rate determining step, 2 molecules involved. Okay, this is E2 elimination. Let's see what's going to happen. Now this is an alcohol. Acid protonates the most basic atom. From the sulfuric acid, oxygen grab a proton, forms a good leaving group, a water molecule. Now the elimination E2, bimolecular elimination. Now there is a hydrogen on this carbon. So this is the carbon that carries the water molecule. Hydrogen is not going to go from this carbon. Instead, it will be gone from the other carbon next to the carbon carrying the alcohol group. Water molecule can act as a base, remove the hydrogen, and then the electrons in this hydrogen and carbon bond gives to this single bond to make a double bond, giving you an elimination product, alkene. Okay. And then you can also see the competing SN2 reaction, alcohol. And so this is our starting material, alcohol. We don't have only one alcohol. There are plenty of alcohols in our reaction medium. And you can see one of the alcohols got protonated in the presence of the acid. So another alcohol now can react as a base or a nucleophile. So it can attack as a nucleophile through backside attack. So this alcohol carrying a lone pair comes to this carbon and leaves the water molecule. So generating a protonated ether. And then see, this has a hydrogen to begin with, this hydrogen right there. Okay. And then the proton dissociation takes place from another water molecule, and you can form the substitution product.